example is also a famous group you've met certainly in quantum mechanics. We call it S1, so you saw that before, that's the circle, but now I understand the circle as a set of points, but as a manifold it's the same, as all those complex numbers Z whose absolute value is 1. So we're talking about the unit circle in the complex plane. Okay? And so this is, yeah. And the blob operation here is now supposed to be the multiplication on the complex numbers. Now you know that if you take two complex numbers lying on the unit circle in the complex plane, then multiplying them multiplies their radii, but they're 1, and it adds their angles. So if this was an angle phi and this was an angle psi, then the sum of the two is here, that number with angle phi plus psi. And you easily see that with this multiplication, everyone has an inverse, and then you go back and forth, and so on. And so it follows that S1 with this, well, I should have written here Rn with its addition, Rn is the translation group, and S1, consider this subset of the complex plane together with the multiplication, is again a commutative Lie group, again a special case, and this is usually called U1. It's the U1 group, that's the group that gives your, well, under which you construct your wave functions to be invariant, because the, well, at least the final results of calculations in quantum mechanics, you want them to be U1 invariant, because you don't want an overall phase to count. Now, so you met this group before. It's a very simple one. Okay. Now, as a final example, we may consider as the space G all the linear maps that take you from Rn to Rn, but that have non-vanishing determinant. This, of course, means that these linear maps are invertible. So I should emphasize here this is supposed to be linear maps that are invertible, and that set has a special name that's called GLN over R. That's the general linear group. Well, it's not a group yet, that's only a set. And if the blob operation is chosen to be the circ, the composition of maps, then certainly I can compose one map with another one, and because the determinant of the map is non-zero, there always exists an inverse, and the identity map is the identity of the group. So we have GLNR equipped with the composition is a, now that's no longer a commutative Lie group, because phi after psi is not generically the same as psi after phi, is a Lie group called the general linear group. And as such is also called GLNR. Okay. So these are all Lie groups. Well, if you have an inner well, let me give you one more example because it occurs so often, but then that should be enough. So assume you have an inner product on an R vector space. So let V be a d-dimensional R vector space equipped with an inner product. Well, let's take a pseudo inner product. Pseudo inner product. Now, what's a pseudo inner product? Well, a pseudo inner product is a map that a bilinear map that takes you from two vectors to the real numbers, all right? That satisfies well, first of all, it's bilinear. Okay, let's emphasize this again. It's already clear here. It's bilinear. And then it's non-degenerate. It's symmetric. Let's first say it's symmetric. That means you have VW is WV. Well, that should say for all VW in capital V. And the third property is that it be non-degenerate. And non-degenerate means that if for all W in V, it is true that V comma W is 0, then it's already true that V must have been 0. That's non-degeneracy. And there is a stronger form of non-degeneracy, and that is positive definiteness. So let me give this as a remark. A stronger